Hello, good morning.
Hi, hello.
Hello. So far, no other student. Any question?
No, so far it's okay.
Okay. Okay, I'm going to wait for more student. Okay, but let's do something.
Okay.
This session is supposed to be question and answer based. Okay, mainly for seeing if some student has some questions. So far, no one come in yet. So I'll go over a little bit of the material for this week. So basically, this week we are more on the differential kinematic and Jacobian matrix, and also the inverse differential kinematics. Okay, these two topics. So let's go from the first one. This one is called differential kinematics. Okay, and Jacobian. So differential kinematic is like last time we focus on the so-called homogeneous transformation metric. So that is to solve the static feature of the coordination static. That means a certain frame with rotation and then with some rotation, and then the other frame, what happened? Okay. But this mainly is for the coordinate translation. So you have some point in here, and then you have some point in here. You actually try to calculate the coordinate of this point based on the original frame. Okay, so try to achieve that. That's called homogeneous transformation metric. And then we have the Denner-Hardenberg metric also for that purpose. But that's actually systematical, trying to find a systematical solution to it. And kinematics, that differential kinematic is like you're not looking at the coordinate anymore. So when you do dx dt, that become the velocity. Okay, that become the velocity. So we talk about the speed velocity or rotational velocity. Okay, so this is the topic of the differential kinematics. So differential is a relationship between the joint velocity and the end effector's linear and regular velocity. So basically, this means that when you have some change on your joint, okay, it can be prismatic change. So how fast the prismatic extend, or is actually rotational speed. How much would it cost the linear velocity change and the angular velocity change, and using the Jacobian metric to calculate it. Okay, these are the topic that today's main purpose. So basically, it's a taking differential on the original one frame calculation. Okay. So here, this different mathematical thing is very complicated. Okay, again, let me bring up the easier version, undergraduate version. Okay, so this one is for the Jacobian differential kinematic. Okay, differential kinematic and Jacobian metric. Okay, we'll bring up these two things. So differential kinematic. This is Jacobian. Let me close this one for later. Okay, so basically differential kinematic. Okay, it's actually looking at the frame-to-frame transformation, but this time we focus on angular velocity and the displacement velocity. Okay. So basically, you take you have the Dennerby-Hartenberg table, and then you form the systematical solution for the transform metric H. Okay. So now you have the relationship on these things, but you try to take derivative on it. Okay. So basically, your t prime will be t plus dt. Okay. T is a frame, and T may have some change, such as this frame move from one location to the other location. Okay, there's a frame transition. So that's dt. So T prime equals T plus dt equals the matrix, your transform matrix, take derivative, okay, and then times T. Okay. This really means that your delta T equals this. Okay, equal this times this. This is actually the metric operations. Okay, that rough idea is like that. Okay, so basically you try to calculate the set of the form. Okay, and then you would find this kind of the differential kinematic metrics. Okay, so first one is let's look at the velocity metric. So velocity metric, if you look at this one and we look at the omega, okay, and omega, you originally have a Dennerby-Hartenberg transform metric, and then if we only look at the change of the angular transformation, the formula would be like this. When you after you take the derivative, you become this, okay. So your original transform would be like this, and you have the ABC. This portion is the rotational metric. Okay, this portion is your positional change, displacement. Okay, and then here is the derivatives. Okay, you actually take the partial derivative on each one of them, and you will get long calculation, and then you will find out the velocity change will have such equations. Okay. And then this metric operation we put into some case study. Okay, so certain frame right here, it has some point, and then the frame is right here, and then your original center has a 2 radian per second rotation. So right here, your base rotator using the 2 radian per second time to rotate, okay, and then will cause how much change over there, and then we set out the formula to calculate it, okay, and get the such a speed. So basically, this whole chapter is on it's doing this, okay, and we do have a Python coding to work on it. You can download the code, okay. So this portion is this one called kinematic, okay, differential kinematic. Then next one is the Jacobian, okay, Jacobian metric. So basically, this for the Jacobian metric is used for velocity analysis for robot. Okay, so Jacobian metric number one, you have a system of the variables that's called joint space, and there is a task space. Okay, so these two, what are the difference of these two? This actually joint space is that you have each joint you have some variable theta. Okay, task space is your end effector, your final finger on the robot would have XYZ transition and the theta phi theta and per c, okay, change. So this is phi theta per c actually is the row. We talk about it is actually the row pitch and the yaw change. Okay, and this is six-dimensional change. So the task space really means your n effectors number variables, and your join space is your variable on the join. Okay, so these two have some relationship. So let's assume that we have a theta input, and then there's a forward kinematic. FK means forward kinematic. You get the output of this task space variable. Okay, and then inverse kinematic should be your task force variable backward to see what kind of speed it is. So backward really is that, okay, I want to go from point A to point B, okay, in certain time. Then how much is speed my rotator, okay, or my extender in the robot arm need to be programmed to. So joint space is the variable for your control of your robot. Task space is how your finger or your arm will be positioned to. Is that okay so far?
Yes.
So this is the two relationship. We actually set up a matrix. Okay, that's what we call it Jacobian matrix. Okay, you take derivative, you call this, and the J minus this one actually is inverse Jacobian matrix. Okay, and then you have, okay, this one actually is original relationship. Okay, so Q1, Q2, Q3, Q4, Q5, Q6. These are the joint variables. So this is a joint variable. Each of the six joint variables, you will have a transform function, and that would input joint variables. Output is your x. Okay, this is an equation of the input and output relationship. So you set up the whole system of the equations. That is this. So this H is your forward. Let's see. Forward kinematic metric. Okay, and then you take derivative. You should get your Jacobian metric. You take derivative, you should get your Jacobian metric. So basically, take derivative of it. Okay, whatever. You would get that each function is DHQ DQ. Okay, that actually is your Jacobian metric. That would become C by N metric. Okay, so that actually is a partial whatever equation that is a Jacobian metric. So then Jacobian metric, they may be linear vector. Okay, the output has XYZ, and these are three angle change. Okay, three angle speed. So basically we divide it into two groups of the output. One is linear velocity change, V vector V, and angular velocity change, that's called omega. So basically your output task space speed will be V and a Q. Okay, it's two things. It's a two vector. Okay, two vector. Okay, so that is the final result. So let's look at this one, a very simple example of two rotary joint. Okay, each one have a robot arm of L1 and L2, and they rotate theta1, theta2. So basically, your n effector xy's and the theta1, theta2 relationship are formulated as this. And we take derivative on it, we will create a Jacobian matrix of this one. Okay, that's when you take derivative, partial derivative on it, you get this one. Okay, and that is what we use to calculate the velocity changes. Okay, so sometimes you have a singularity. Okay, the singularity happen when your what Jacobian matrix determinant is 0. When will this happen? This happen when you actually sweep like a baseball bat. So theta 2 not changing. When your theta 2 not changing, it's actually just like a one-dimensional change. So theta 2 no change, you mean this actually is all zero over here. That's what we call it singularity. Okay, so because of the singularity, some location we may not be able to found. So it's a not full rank. It's not 2D anymore. It's one-dimensional. So you take the derivative of the Jacobian metric, take the determinant of the Jacobian metric, you get zero. So that actually is one way to check whether your robot can still get the two-dimensional degree of freedom or not. Okay. Suppose they are two variable, you should, but if your theta 2 always no change, then you get the determinant of the Jacobian metric should be zero. Okay, so here we do have some calculation about the pseudo inverse, okay, of the Jacobian metric. Okay, but that is to handle the singularity. Okay, anyway, so Jacobian metric operation can be systematically done, okay, using some transformation. Okay, so one thing you must know is the cross product. You have A, B, C, vector A, you have vector B. Then you create cross product vector C that is using the cross product. Using the right-hand rule, you create a cross product. It's called A cross B. Okay. And IJK is the unit vector on the coordinate. Okay, on the coordinate. And then anyway, this one will get this direction product. Okay. So that actually is a mathematical function you need to know. So Dennerby-Hardenberg transform metric, each or one of them can be written as this. Okay, cosine theta I, cosine alpha times sine theta I. Okay, whatever it is. We use C for cosine, S for sine. Okay. And then we want to calculate the Jacobian metric. It become this. Okay. So what this reason really mean is like, okay, we set up the Dennerby-Hardenberg metric, and we set up the transform metric of A1, A2. Okay. And based on this A1, A2, we try to derive the O vectors, O0, O1, O2, and the T vectors, Z vectors. Okay. And those O vector and Z vector in combination should be able to solve and get your Jacobian metric. So here we set up how to calculate the Jacobian metric. Okay, using those O vector and the Z vector, whatever. Okay, so at the end we get these. We have a Dennerby-Hardenberg transform metric A1 and Dennerby-Hardenberg transform metric A2. And then we calculated T01 and T02, okay? And based on T01 and T02, we derive the different O vector and Z vectors. And then in combination, we should be able to come out with a systematical result for the Jacobian metric, okay? J1, J2 vector. And we do have a Python example that can do it, okay? So there's application. There's one more lab you can look at it. It actually is doing calculation for one example, how to calculate a forward kinematic, okay, from the Jacobian, and there are some the linear and the revolutional Jacobians calculation. Each vector of the G, how can we use a cross product to create that? Okay. And this has a long derivation on it. So you have to watch the video we have, okay? But anyway, the end result is you will use that to find the Jacobian matrix, and that can be used to solve the former forward transform matrix. Okay, so this is relationship of Jacobian matrix. And then there's also possible that your join are all prismatic join, and we derive some the equation for it. Okay, and also possible you may have the all revolutionary join. We also derive the equation on each one. Okay, this every single one is very complicated, so we can only quickly go over. Okay, and the equations like that, and based on that, you can use to look at the Stamper manipulator, 6-dimensional manipulator, and then it's a RRP. RRP is that rotational, prismatic, rotational robot. So here one extender, everything else are rotational. Okay, and you set out the equation for each one of the rotation, and then you got the long calculation, and then eventually you have the Jacobian. Okay, that's what this chapter is. And then there's an inverse Jacobian. And the inverse Jacobian is based on the Jacobian metric. Okay. And you do calculate the inverse Jacobian based on the equation you have on the Jacobian. So you do inverse transform of the original metric. You got the inverse of it. Okay. And that actually goes through some calculation, also very complicated numbers, and eventually you come out with such equation, and then can solve the inverse Jacobian. Okay, so based on this inverse Jacobian, you can use to control your trajectory path. Okay, inverse means that given me some velocity change. Okay, what kind of the given me some path, what kind of joint variable I need to have. Okay, so that actually is a number that used to control your robot state variables, the robot joint variables. Okay, so basically that's the purpose of inverse Jacobian. Given me the destination XYZ change, what kind of joint variable I need to have. So that's called trajectory planning. So that actually is the purpose of calculating the Jacobian inverse Jacobian metric. Okay, so that's what this week is on. Okay, and that is there are a lot of problems. Any questions so far?
No, it's okay. Yeah, very interesting. Yeah.
Yeah. So basically, I just go over the concept of why this metric and inverse metric need to be. Okay. And one problem we do have is like the quiz 3A actually a few students are low. Okay. And this actually happen every year. And this set actually is one of the easiest one in the course. And why is every year student doesn't do well on the quiz 3A? That is because quiz 1 and 2 are easy. But when students jump to the quiz 3, they may not be well prepared. Okay. So usually this one is they don't get well every year. And then 3B and 4.
Because we need to do a calculation or something or no?
More calculation, yes.
More calculation, yeah. Okay.
Yeah. So that's usually why it's not doing good. Okay.
Okay.
So I'll look at overall grade, and then later to if something need to be done, like given one more try. Okay, maybe I'll look at it, because right now we only have 5 out of 9 submitted. Okay. Let's wait until everybody submit before we if nobody submit, right, then there's no meaning of adding. If not everyone submit, right, there's no meaning of adding one more try, right? Why not? Because some students even didn't finish the first 2 tries, so there's no reason that we give them 3 tries, right?
Okay.
So I'll see. Okay, I'll see how the whole class do over there. Okay.
Okay.
Other than that, I think okay. The programming assignment I'll grade them this week. Okay. Today or tomorrow. Any question?
No, it's okay. Yeah, I have to submit my week 1, 2, 3. I'm kind of a little delay, and I submit my for the final project.
Take your time, okay? We do not want to rush you, so
okay.
I say we don't deduct because it's only an 8-week course, so we don't deduct any point for late submission. But we don't encourage students to pile up a lot of things, right? That's also true. That when you pile a lot of things, you cannot catch up because there are really a lot of things to do, right?
Yes. And for the final project, you are gonna send us a feedback if it is okay or not, the proposal?
Proposal, usually I will just look at your direction and how much you have done, okay? As for the topic, as for the project, unless that you are totally not related to robot, usually it's okay. So we actually give you the freedom of choosing the project, okay? As long as it's related to robot, we will accept it. And I'll grade them today, okay? It's a proposal. I'll grade them today, and then we'll see.
Okay, sounds good.
Okay. Any other question?
No, it's very good. You provide a lot of documentations and
a lot of things to starting. Okay, so this course is tough, but my principle is that I try not to grade too harsh. Okay, I try to be nice on grading, so be flexible to work on the project and everything. Okay. And that's the way to learn, right? We don't want to give too much penalty. So usually some of the programming assignment, if your answer is 2.1 versus 2, we don't deduct it, okay? We don't actually deduct a point just because you missed 2 digits or 1 digit, right? Actually, it makes no sense. So we just look at the overall calculation. Are you really sure that you are doing something related to what we are talking about or not? Okay.
Okay.
That's but the detailed calculation or the formulation or coding, it's very easy to get something wrong, right? It's very easy to get something wrong. So the purpose is that making sure you understand what is the purpose we are doing Jacobian, what is the purpose that we're doing inverse Jacobian, what is the purpose we do a homogeneous transform metric. Okay, that's the more important. And also that's the purpose of the course, right? Is to making sure every student knowing what are the calculations. Okay.
Okay. Yeah.
So, but these are Jacobian, whatever, they can be applied to machine learning or something else as well. Okay, it's not just for robot arm calculation. Okay, there are a lot of things that you can apply to. So, make sure that you understand those math. Okay.
Okay.
Okay. Any other question?
No, for me that's all. Yeah.
How about Nathan? Do you have questions? Hello. Hello. Any question? Okay. If no question, we go over everything I want, and then I'll grade and provide a return for this week, today or tomorrow. Okay, to finish everything that I see on this to be graded part. Okay.
Okay. Sounds
okay. Then that's it for today. Okay.
Okay. Thanks so much.
Thank you. See you next time. Bye bye.